everybody. Today we are proposing an idea for our sustainability class about, and we're proposing the idea of a wind turbine in Teras FTMD. Next slide, please. So we are as a group. There is me, Amabel, Ariandi, Wildan, Rumi, and Handaru. So before we jump into the technical details, we need to know why do we need to do this project. Teras FTMD now already demonstrates the application of sustainable building design through the use of solar panels and a slidable roof system. These features show that sustainability at Teras FTMD is not only conceptual, but already implemented in its architectural and energy systems. Building on this foundation, the installation of a vertical wind axis turbine would serve as a natural extension towards a hybrid renewable energy system. Wind energy complements solar power, especially during cloudy, rainy, or low sunlight conditions, allowing energy generation to continue even when solar output is reduced. In terms of technology suitability, VAWTs are particularly appropriate for the urban and architectural context of Teras FTMD. They are capable of operating at low wind speeds and under turbulent airflow conditions, while producing relatively low noise and minimal visual impact, making them safe and suitable for a campus environment. Beyond energy generation, the VAWT also provides a strong educational and research value. It can function as a real-world experimental platform, enabling students to observe, measure, and analyze wind energy performance across multiple disciplines. From an institutional perspective, the presence of a visible wind turbine offers a clear public relations and branding advantage. It strengthens FTMD's image as a forward-thinking faculty that actively implements sustainable and innovative technologies. Overall, the installation of a VAWT represents a low-risk yet high-impact sustainability initiative. Even with modest energy output, its combined technological, educational, and symbolic benefits significantly enhance the role of Teras FTMD as a living laboratory for sustainable development. Next, please.
Okay. Okay. My name is Rumi, and um, I'll be talking about the tool, which is choosing the turbine type. So rather than using a conventional horizontal turbine, we have selected the vertical axis wind turbine, the VAWT configuration, specifically focusing on Savonia's designs. We choose this specific tool because it offers three critical advantages for a campus environment. First is omnidirectional capability, allowing us to capture wind from any direction without a yaw mechanism, which is essential for the turbulent airflow found in urban settings. Second, we VAWTs operate with a much lower acoustic signature, making them non-disruptive to the academic atmosphere. Finally, from a safety and aesthetic standpoint, these units are far more suited for integration into public spaces like the FTM, the Terrace. Uh, if we want to compare the two between a traditional horizontal axis and a Savonius design, we can see that the wind direction requires the yaw mechanism, of course, while the VAWT has omnidirectional, which can take wind from any point, and the noise level is clearly lower, while the one for horizontal axis is much more noisy, which can disrupt the academic um, atmosphere in Terrace FTMD. And then we have the urban suitability, which is way more preferable than the horizontal axis. And it is safer because the speed is slower than having something as fast as a horizontal axis. Next slide.
Okay, so here are the challenges we met when trying to implement a wind turbine into Terrace FTMD. So from a data which we gather from a meteorology station near ETB, it shows that the wind in the area is very, very slow. It's fairly slow that it is not enough to actually start up the wind turbine, which needs a minimum speed of 1.5 meters per second. And so here, the turbine will not generate any meaningful power because the rated wind speed of Symphonious design wind turbines are around 11 meters per second. But we have a solution, which is implementing an omnidirectional guide vanes, and according to some research, this kind of guide vane could increase power coefficient of turbine for up to 48% and lower its cut-in speed for up to 1 meters per second, thus increasing energy production, and the turbine can now generate meaningful power. So, what are the impacts of having a wind turbine in Terrace FTMD? So, to calculate the impact, we need to know how much carbon emission can be cut from using this turbine. So first, we calculate the power output of the wind turbine. Each wind turbine will, on low wind, will generate around 0.37 watts, and on average wind, which is around 2.2 meters per second, it will generate around 1.16 watts. And on peak wind, which is around noon at 12 p.m., it will generate around 5.08 watts. So the daily energy yield each turbine, duration of the low wind will be around 4 hours, and the average wind will be around 4 hours, and the peak wind will be around 1 hour. So the total energy yield per day is around 11.2 watt hours per turbine. So if we have 10 turbines installed in Terrace FTMD, it will generate around 41 kilowatt hours every year. And this is equivalent to a carbon emission of around 35 kilograms of carbon dioxide. And this is assuming that power plants in Indonesia will have a carbon emission of around 0.9 kilograms per kilowatt hour.
Lastly, the vision. Net zero energy refers to a system where total energy consumed over a period of offset by energy produced from renewable source on site. This concept shifts energy system from centralized fossil-based supply towards decentralized low carbon solution. Rather than remaining a theoretical concept, this project translates NZE principle into a functional system operating in a real campus environment, allowing performance and limitation to be directly observed. By generating energy locally, the system reduces reliance on external grid electricity, lower transmission losses, and decreases indirect carbon emission associated with centralized power plants. The project serves as a testbed for scalable renewable solution that can later be replicated across the buildings or facilities on campus. Next. Here we have microgrid based autonomous charging station. Uh, this microgrid based autonomous charging station would provide solar PV and battery from standalone microgrid, supplies power for laptop and phones charging at student terrace, operates independently from the main campus grid, reduce peak load, and support NZE targets. Next. Also, we want to make this project like a living laboratory concept. This project will provide installation double as a real-world learning platform. A student observe actual renewable energy behavior, enables hands-on learning beyond simulation, and system data available for experiment and analysis. I guess this is the last section of our presentation. Next will be closed by Abel.
Okay, based on the presentation, we have concluded that our project is very, very supportive to the sustainable development goals. And we hope that this project can be realistically done by FTMD. So thank you for listening. We hope the best for the world. Thank you very much.